So, Assalamualaikum. Hello, everyone. I am Hasanul Himel, your friendly community contributor. Uh, First, let me check if you are able to hear me or not. Okay. Yeah, we're live. So, today I have a special guest with me. We are currently in the age of generative AI and we're learning more things day by day. So, till date, if you were connected with me along from past 1 year, you would know we learned about the basics of machine learning. We learned about deep learning. We discovered about LLM and stuff. But in today's episode, we I am going to introduce with someone and the person who built something amazing, at least amazing to me. So in today's session, we will be discussing about vector database. So I have Adib Mohsin, the founder of Antarys AI, with me. I would like to invite Adib to the stage.
Hello, everyone. Thank you, Himel, for introducing me. And yeah,
So if you have any queries, you can drop down in the comments. And in the meantime, I will also share some things or ask some questions to Adib, and uh, now I have a little bit of knowledge in vector database, so it will be a learning phase for me too. So, Adib, would you love to introduce us with your creation, the Antares AI?
yes, absolutely. So, first, I'll go through how I began on um, working, or basically, where did I get the idea of building this? So, it's actually a very funny story. So, Brack University, Himel, as you know, they teach Java, and I don't really personally like Java, to be honest. It's a very personal opinion of mine, but yeah, I don't like Java. So I had this plan of, like, I was doing a lot of the assignments with the help of ChatGPT, mostly because of the fact that I don't really like Java, right? So I was thinking to myself that, well, what can I do is I can just ask my computer to do the assignments for me and upload the whole thing to the Brax website. Like, yeah, I'm pretty much like committing to some corny things on live, but yeah, I was thinking of doing something like that. Like if I just had a bot that would do it for me. So in pursuit of that, I started working on like a very it was something like my own personal service where I could talk, where I could give it some input, like, yeah, just go to the Brax website or just scrap over my assignment, read whatever the questions are and solve them, and just format them properly and just upload them. So I was pretty much trying to do something that was offline, that would listen to me, and that would like understand my behavioral patterns and just try to mimic me, but digitally. So one of the one of the possible routes I could take was either I could teach a model to be like me, which would take a lot of computing power, and I'm gonna have to train my very own small language model, and then I would have to train it to be able to take actions. That would just be too much, to be honest, because first of all, it's quite costly to be able to at least build your own model from scratch. And the other thing that I could do was I could try to build a RAG application, something with like LangChain or something like that. I could probably hook in a package called PyAutoGUI, which I love, by the way. It's really great for automation, or, just controlling the mouse or keyboards. So I was trying to build a RAG, and then I was trying to introduce a very fast vector search into the application. So the problem with the current vector searches are, if you have ever done vector search before, So most of the people use something called FICE, and FICE is really great, but it's not really built for huge amounts of data. And then there's another one. It's called ChromaDB, and ChromaDB doesn't really scale well if you have more than 1 or 2 million documents. So I was kind of in a position where I was thinking about, well, I could just build my own vector database from scratch to be able to support myself building a tool that would help me complete my university assignment. So this is where I started almost 6 months ago or 7 months ago. I don't really remember. But after that, I got into building the vector search. And the other fun fact I found about how large language models or small language models work is that they store most of the data in like very high dimensional spaces. So I was thinking about what if I could build a pipeline where you have all of this raw data, like, right? So you take in this raw data, you basically assign numbers or basically vectorify them. So by vectors, by the way, in computer language, vector means one-dimensional floating points. So you can pretty much represent any sort of data in like floating point numbers, right? So what if I could take like raw input, vectorify them, and then store them in one single pipeline? So yeah, this pretty much this whole idea of building such a system got me into building Antarys, to be honest. So this is how I started working on the whole system.
Okay. So we have a comment from one of our viewers. Do you like to take that? Let me just pick.
Who inspired you to? Who inspired you the most during your journey to Antarys AI? Yeah, this is actually interesting. There's this guy. His name is. Let me just Google him because he's known as the first guy to ever hack Apple or the iPhone. Yeah, his name is George Hartz, and he's probably one of the most crackhead engineers I've ever seen. So he's the first guy to ever hack an iPhone. He's the first guy to hack into the Sony PlayStation. When Sony sued him, he literally dissed Sony via a rap song. So he was like an amazing guy, right? And he has this OCD to pretty much build everything from the ground up, right? So he loves to build everything from the ground up. If you talk about machine learning frameworks, if you talk about game engines, if you talk about pretty much anything, he builds everything from the ground up. So that's his motto, that's his way of doing things. And right now he's working at a company. He founded a company called Comma AI. So they are kind of like the open source version of Tesla's autopilot. So I've been following this guy called George Hartz. I would suggest anyone who is like really interested into becoming a crackhead programmer, like just coding all day, all night. I'd suggest anyone to follow this guy called George Hartz. So yeah, this one guy really inspired me, and the other one would probably be, yeah, Elon Musk at this point is a bit of an overhyped person, but yeah, the way he thinks about products is it's just different. Yeah. So I think that really answers like who inspired me the most. These two guys are amazing.
So, do you like to give us a walkthrough of your project, like how this actually works? A real life demonstration.
Yeah, sure. I think um, what how it should make it much more easier to understand if I really just explained you how vector search actually works, right? I think
Yeah,
that
sure.
is something a lot of some people have some confusions about, like what is a general search, like we can just search via texts or keywords versus what is a vector search, right? So if first of all, the reason why it's called a vector database is because vector database and let's just take something like a SQL database, right? So MariaDB or MySQLDB or whatever. You have all of your data in structured positions, right? And you know what? I think it would be much better if I just showed you my screen and just did some pseudocoding. I think that would just make it much more easier, to be honest. Yeah, I hope you guys can see my screen. I think you guys can. So if you take something like MySQL, or if you take something that's NoSQL databases, so for example, MongoDB, right? So you have all of your data that are completely structured. So you have something like name, which can be a string, and then you have something like age, which can be a number. So all of these data, they're very much structured, and the way that you store this data are through programming, right? Basically, you have forms, you have things called ORM. So these are like object relation mappers or management. I actually forgot about what these are, but you have to store this data in very structured manner. But what if you have to query for unstructured data? For example, what if you need to query between images, or what if you need to query between, let's just say, a video, right? So vector searches are very different. Instead of data that looks like this, like structured data, you actually store numbers that are basically floating points. So 2.0, 3.0, stuff like that. So imagine you have an image. For example, I just took an image of this water bottle, right? And when I vectorify this data, that raw image turns into a vector, right? And it also holds something called a metadata. So the metadata could be something like water bottle. And this thing then gets stored into a vector database. So vector DB storage. So for now, just imagine that this thing being stored inside a vector database. So when you actually query something, like for example, you query another image, right? So you query something like another water bottle. What happens is that this is the data, right? And you're actually querying not against any of this metadata or anything. You're querying actually against the numbers. So your query could look something like 2.0, 1.0, and something like 2.123, whatever. What happens is that the vector database takes your numberified or vectorified query and finds similarity between numbers. So this is very much revolutionary, to be honest, because in normal databases, what you do is you query against the data structure itself. So you get pretty much the similar, you get actual result, right? So you, for example, if you query for an email or password, you'll get the exact same thing. But vector databases don't really return you the same exact thing. It returns you things that look similar in vector spaces. So if you represent something like an image in a in higher dimension numerics, what you will basically get is something that is supposed to look like a water bottle. So, for example, this works for any sort of data. You can turn, you don't have to really use a raw image. You can always use something like a raw audio. So, what's going to happen is that you will take something like my voice and you'll input it directly into the vector database, and it will just store the numbers, right? And when I query something like Himel's voice, so it's not going to really say that, yeah, this is probably Adib. It's just going to return me something like, yeah, I don't know who it is. But when I again query with my own voice, it's going to say, yeah, this is the voice of Adib. So if you then scale this up to images, scale this up to audios, you scale this up to videos, you can pretty much query anything. So this is really amazing. You can build lots of applications with this. For example, Pinterest uses this for similarity image, and then Shazam uses this for pretty much finding out like what song you're listening to. Spotify uses this to be able to recommend you some songs, right? So this is basically how vector databases work in a very, very high level manner. And there are a couple of ways vector databases find these similarities. These are like some mathematical concepts. So first one is, it's called cosine similarity. And there's another one, it's called Euclidean distance. And there's another one, it's a very new one, but it's called topological distance, topological similarity. Yeah. So these are basically the primary similarity finding algorithms that are used for vector databases. But the one I'm using, it's called cosine. So yeah, before I get too technical, do you guys have any confusions, or I think I'm getting way too technical at this point. So uh, yeah, you're muted, Himel.
My bad. We have another question. Let me copy that.
Okay.
What are the unique features of Antarys AI that differentiate it in terms of performance, availability, or usability?
Okay, before I move on to Shakil's comment, let me answer this one from Fiona. So, yeah, uh, I think I need to go back to my screen presentation. I think, Himmel, you need to go backstage for people to see my. Yeah. Yeah. Okay. So let me show you something. It's called GIL Python, and let me pull up something else called thread locks. Right. Okay. These are not the thread locks I was looking for. Thread locks. Let's just go for Golang. Or I think it should make sense. It's called a mutual execution lock. Okay. So, so Fiona's question was, what makes Antarys different from the other vector databases? Most of the vector databases use something called HNSW. Okay, so it's the algorithm that really, so it's a graphing algorithm, and the way that I'm showing all of this data, right? So like I showed you that it's just one node of data, right? So you have an image that is the image of a water bottle. For example, if you have, let's just say, 10,000 documents or 10,000 images, what HNSW does is that it creates something like a map or something like, just imagine a small world where everything is connected. Okay, this is, I think, a better example for this would be KNN. Yeah, so this is a much better example. So uh, in the real world, let's just say that I go to a market, and this is a furniture market, right? And when I see multiple sofas together, I basically know that this is the section of sofa. And when I see a bunch of beds, I know that this is the section of the beds, right? And then I see a bunch of tables put together. I would naturally think that, yeah, this is the section for tables. So you'd see that all of this data are clustered. All of these things are clusterized, right? So there's this one section of sofas. There's another section of beds. Another section of full of tables. So as you can see, that these things are positioned very much together in a clustered way, right? And these things are not connected, but at the same time they are quite connected. So all the sofas, these are data nodes that are connected to sofa-like data nodes, right? And all of these beds, they're connected to beds, right? So these all look similar. All the beds look similar. All the sofas look similar, and then you have all the tables that look similar. So these are segmented or clusterized data. And the way HNSW works is that, just imagine a small world where you have basically layers of data, and these data are clusterized together in terms of similarity, right? So, for example, when I take an image of, so for my vector database now is going to store some image data. So I have an image of a bottle, and I have image of multiple other bottles, and then I have an image of my phone, right? So what happens is that in a vector space, these data they are linked together, but the distance is very much far ahead, right? So if I now query another phone, the data is going to point to my phone that is stored in the database. So this is a very much graph structure. So, and this in this graph structure, we have all of this data segmented into places. So these are clusterized data. So a good example, so a good example of this would be the KNN, or another would be K-means clustering. So what happens is that when these data are inserted, these data then are based on their behavior or based on their data points, they're pretty much stored in high dimensional spaces like this. So, like I said, for example, this could be my phone that lives around here, and the water bottle image could be living around somewhere here. And this would be labeled as, like, for example, this could be the section of water bottles, and this could be the section of phones. So this is much more. This is a completely. This is a good example of KNN or K-nearest neighbors. And the algorithm that powers all the vector databases, it's called ANN. So not artificial neural network, it's called approximate nearest neighbor. So the difference between KNN and ANN is that KNN gives you the exact same result that you were looking for, which means that you're going to have to brute force between all of the possible data, right? So it's kind of like, again, I'm going to pull up the furniture example, where I am looking at all of the data, all of the furnitures independently to find out, yeah, if I'm looking for a bed, right? So I'm trying to look for a bed. I'm going through the section of sofas. I'm going through the section of tables. I'm going to the section of beds. And yeah, I wanted to buy a bed. So yeah, here it is. But Canon, that means that it's brutally slow. The I'm not really sure, but the complexity, algorithmic complexity of Canon should be ON. If I'm, then again, I'm not sure. But if you do something like ANN, approximate nearest neighbor, what it does is that it finds you something that's similar, right? So, for example, again, I'm in the furniture showroom, and I'm looking. I want to buy a bed, right? So, in a very high level view, I already know that this section is selling beds. So I go to this section directly. So this is called HNSW entry point, right? So yeah, you're gonna have to dig much more to be able to like find this stuff out. I actually have written an article about this. So if I just go to research HNSW, I think this is a much better high-level overview of how HNSW works. But I basically find an entry point to be able to start looking for data. So I go directly to the section of beds because I know this is what I'm looking for, and then just start finding, like, yeah, this is probably similar to what I was trying to look for. So this is basically like a very, I don't know if it was a good example or not, but it's a very high-level overview of how HNSW works. So the reason why I was talking about this is because you're gonna have to understand like exactly where the optimization is actually coming from, so you can really complement where Antarys is much different from all the other vector databases. So yeah, when I was so when you do a query, it goes through all of the data nodes, right? And ANN is a bit different than KNN because it only looks for similar things. But even though it looks for similar things, it has to traverse through all of the graphs, all of the data nodes in the graphs, right? And it has to constantly map out a similarity factor, and then pretty much like calculate like if this data is similar to the data you queried. So when you're, for example, going through a document that has like 10,000 or 20,000 graph connections, so graph connections look something like this, in a graph data structure, it looks something like this. Yeah, this is a very accurate picture of how graphs look in a two-dimensional view, right? So when you're traversing through all the nodes, what happens is that in in an environment where you need performance, vector databases love to use multi-threading, right? So uh, you have multiple threads trying to look for the same thing, and what happens is that you're pretty much copying over lots of data over memory when you are going through when you are looking for the same data from multiple threads. So this brings in something called mutual exclusion lock, because just a second. Yeah, I'm nerding out a lot, but I think these are like really important computer fundamentals. So when you're basically traversing through a lot of data, and you're also doing multi-threading on top of that, what happens is that you might write the same data twice in two different or multiple different threads. So that creates like that really corrupts the memory, that can corrupt the data structure by itself. So in order to avoid that, what happens is that programming languages or computers have something called mutexes or mutual exclusion blocks. So it basically says the other thread to stop and let me override the data first, and then you're going to have the chance. So what happened? This is very important for this is very important for multi-threading applications, because you don't really want to corrupt the memory, you don't want to corrupt your data, and you obviously do not want to overwrite the same data again and again. So I think, yeah, I'm going to have to bring up much more examples for me to explain like why we do mutexes, but this is basically the high-level overview of what happens during a mutex, right? Antarys is a bit different. It was written in a way where you don't really need to be able to use the thread lock much as the other vector databases. So most of the vector databases use thread locks to not corrupt the data. What I've done is that it's basically a trade secret at this point. I have found a way to be able to kind of avoid locking the thread, but instead use very this is much technical. It's called a memory pooling. So what you basically create is a pool of accessible memories. So this is basically some of the ways that I have done it. But if I were to tell you like what really affects the performance of Antarys, is that I do not use thread locks. It happens. The data is still pure. It's not overwritten, and the way that it happens, well, this is the part I'm not really supposed to give out. So yeah, so this is like how you would imagine, like for example, if you had a Python program, you have something called Python threading, right? So thread-based parallelism. So in a nutshell, how you basically write multi-threading applications is that you have one function that is just taking way too much time. So you want all of your functions to run at the same time, right? And all of them are writing over a same variable. So for example, if what's going to happen if two threads access the same memory or access the same variable at the same time and write over that, it's basically going to corrupt your result, right? So you're probably not going to get the expected result. It's going to create bad data. And to avoid this, what Python or many of the other programming languages does is it uses something called semaphores or mutexes. And Antarys doesn't use this thread locks. I have done something very different. So it's not really something that I have done with the algorithm by itself. The algorithm pretty much stays the same. It's just the way that I've implemented in Antarys that is different. So yeah, I'm not. Then again, these are all very like technical standpoints. If you have any other confusions, just let me know. To be honest, yeah.
We have another query.
Hi Shakil, which language are you using to build your feature database? Does the choice of language affect performance? I read somewhere Pinecone was written in Rust for better code performance. Would love to hear your thoughts. Yeah, obviously language matters. So you have something called DSL, right? So domain-specific languages. For example, C was written entirely for systems-specific work, like building operating systems, and then you have C++, which are like much more industrial-oriented program languages. for building like really performant applications like game engines and stuff like that. Then you have Rust, which is a good one, but I don't really personally like Rust. So yeah, language does matter. If specifically for applications like this, low-level languages are much more better. So yeah, Antarys is using Go, but the reason why I picked Go is because, well, I wanted to really build out my MVP, or basically the prototype, really fast. And it's not really a prototype anymore because all the optimizations are very solid. But I am probably going to move from Go and switch to Zig. Zig is a much more, it's a systems language. It's a much more low-level language than Go. The reason being that Go has something called a garbage collector, and I really want to be able to like have much more memory precision control over my database. So yeah, language does matter. Language is very important for building stuff like this. I think you can pretty much build anything in any languages, but if you're building something for production, language does matter. For example, WhatsApp uses something called Elixir and Erlang, right? So they could have easily used something like C or Rust for much more better fine-grained performance. But then again, Elixir was built for really real-time heavy applications like this. So yeah, you really have to understand why DSL exists and why DSL actually makes a lot of sense when you're building serious production applications. Yeah.
We have another final query.
How does Antarys AI handle challenges like high dimensional data, vector updates, and hybrid queries? Uh, if you are building something like a vector search, these are basically the expected challenges that I have to face, right? So, how does Antarys AI challenge high dimensional data? I didn't really get your. I'm sorry, but I didn't really get the question because, like, what you described is basically the job or the function of a vector database. So, if we're asking for how did I do it technically, I'm again going to have to introduce you to something called HNSW. So HNSW is basically the graph that holds the data together, right? So you can, I have a very detailed article written on it, and you also have an article on Pinecone. But yeah, this is basic. HNSW is basically a fancier version of graph, to be honest. And the way that I measure the similarity between all of these data points, it's done through something called cosine similarity. So let me give you how cosine similarity actually works. I think that could also clear up the confusion of how search happens inside a vector database. Is that you have XY. Yeah, let me just see myself. Yeah. Okay. Yeah, this is fine. Okay. So you have, like, for example, a a graph like this, for example. So this is the x-axis and this is y-axis, and you have two data nodes here, right? So what happens is that we use something like Euclidean distance in order to directly measure the distance between two data nodes. So that's called the Euclidean distance. And there's another thing. It's also there's another distance measuring algorithm. It's called Manhattan distance, but we're not going to cover that up because I personally don't. I've forgotten what Manhattan distance, how Manhattan distance works. But the way that cosine similarity works is that it measures the distance of two data nodes in a higher dimensional space via measuring the delta theta. So it actually measures the angle difference between two data points. So if that makes sense. So this is how cosine similarity works. And if you're asking how do I handle or how do I manage, sorry. Yeah, how do I manage high dimensional data and hybrid queries? Yeah, I'm going to get to hybrid queries just now. But for high dimensional data, this is done through a graph data structure. And like I said, it's called HNSW. I'll link it up if you guys want me to. But yeah, this is practically a graph algorithm that pretty much just holds data points. And these data points hold something called vectors, right? So again, in computers, Vectors are one-dimensional array of floating numbers, right? So just imagine, like my hand is a graph, and this is another graph, right? So all of the fingers are, um, yeah, all of the fingers are supposed to be the data points, and all these fingers are supposed to be data points, and these data points have two data. One of them is the vector itself, and the other one is the metadata. So the way that you can actually label the data, right? So you have to represent these numbers via, yeah, I'll get to that. Uh, you have to label these numbers via some sort of identifiers. So this 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 is how vector databases or vector graphs look in a higher dimensional way. So the furthest part are not really the similar parts, and the more you go down below is the most accurate search you get, right? So these data live in a higher dimension. So this is what I've been talking about. You have to really study HNSW because it's a very theoretical thing, but this is a very fancy graph algorithm that is not really 2D. It's just imagine this as 3D, and all of these fingers, like I said, are vector points. And when a search query happens, it goes through each layer, right? It measures each vector data and does the similarity calculation on top of that, and it sees like, yeah, if this data is similar, if this data is similar, nope, if this data is similar, nope. And what happens is that it goes to this point and it basically removes this chunk, right? So this, imagine this hand being a data cluster. So basically goes to another level, and it considers that, yeah, the search item is not available in this floor. What I need to do is then look for data that are inside this data cluster, and then, yeah, it measures all of the cosine similarity again. And again, I'm going to go back to Fiona's question, is that what really makes unique Antarys? What really makes Antarys unique is that when you're traversing through all of this data, right, you're pretty much looking, you imagine a lot of workers looking into data. And what happens is that, yeah, what happens is that other vector databases like Chroma or Pinecone, what they do is that they create a thread lock. So imagine that, yeah, you can only look at one data at a time, right? Even though they are happening in multiple threads, you can only look at one finger at one time. But Antares does not have this limitation. It does not create thread locks, and it does not enforce this thread lock on search traversal. So what happens is that it moves around freely per finger searching or per vector node searching. So yeah, I think we can. I think I've answered Navid's question, but then again, oh, sorry, I forgot about the hybrid queries. So I've been talking a lot about numbers, right? I've been talking about that vector data are basically numbers in high dimensional points. But how do you convert something like, yeah, this raw image into numbers? So that happens through something called embedding models. So you have multiple projects in Python. I'll show one of them. It's called Fast Embed. And then you have OpenAI embedding. So yeah, you have multiple embedding models, and I think there's also one from Cohere embedding. So you cannot just turn any data randomly into numbers, right? So for example, large language models actually need to make sense about what sort of data that you are querying. Otherwise, it wouldn't really know how to exactly find your data. So just imagine that this is a translation that's happening between me and a Chinese person. So for example, I'm the Bengali guy here, and I need a translator between me and the Chinese guy I'm trying to talk, and he needs to be able to know Bengali and Chinese at the same time. So this is very true for embedding models. What happens is that it takes in the raw data. It's 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 kind of like a large language model, but it's kind of like the inverse of large language models. It actually, instead of uh, instead of generating text, it instead generates the vector embeddings that are readable by large language models, right? So it takes in the raw data and it then converts it into high dimensional vector embeddings. And then those embeddings get stored onto the vector database itself. And when you query the same things, it gets fetched from the vector database itself. So yeah, you're gonna have to pass through your data to an embedding model, and this is what I've been working on for the last couple of days, is that I'm trying to build an embedding service into my application. So it's not just a vector search database anymore. It's also going to be a place where you can pretty much turn your raw data into embedding data, and then you can also store it, and then you can build applications with it. So it's kind of like a whole AI infrastructure stack. And if you're thinking about if all of these vector embedding models are open source or not, a lot of them are. A lot of them are proprietary, like Cohere's ones. I think there are paid versions. So you might be wondering, why do I need to pay? For example, if you are a bank, or let's just say a hospital, and you have abundance of large data, right? So you're actually going to need like proper data centers or proper hardware to be able to convert all of this data into higher embedding data. So yeah, this is how you do it. You can do it offline on your machine, but it's only for building hobby applications. If you're thinking about large scale, you're going to have to use something like Cohere. But Antarys is going that way, so you're probably going to see like Antarys cloud models that will be able to uh, convert all of this data into higher embedding data. And this is very similar for embedding image. So you can also create vector embedding for image. So yeah, there are models to be able to take your image data and then convert it into high dimensional space, high dimensional dimensions. Sorry, high dimensional vector data. So yeah, it's just really about which sort of model that you want to use. But vector database just store the vector data itself, and you're gonna have to generate it from a vector embedding model that is again freely available on the internet. You have multiple open source ones and you have closed source ones. So yeah, it depends on what sort of service you're actually looking for.
We have one last query, and after that, I have some my personal queries to you.
Yeah, sure.
So at first, just answer this, and then I think we should continue.
Yeah, Ubaidur Rahman asked in RAG, uh, what's the bottleneck, the model or the database? This is a very interesting question, because uh, performance doesn't matter if you're building something that's not super scalable, right? So, for example, even if you're serving, let's just say, 10,000 or 20,000 customers, you don't really need to think about performance that much. Uh, okay, this is a very how, I cannot really put it in a very small yes or no answer, so I'm gonna have to explain it a bit. So if you're building a RAG, right, and let's just say that you're building a RAG for a law firm, or yeah, let's just say a law firm, and you have to iterate through 1 million PDF documents, let's just say. So in positions like this, performance really matters, because well, Antares gives you the most search performance out of the box. So this is where you can actually save up, or you can basically see like 20 or 30 seconds being constrained down to, let's just say, 8 seconds. So for really large enterprises, this performance benefit actually is going to save them a lot of cloud infrastructure costs. So first of all, the first benefit that you're going to see from a vector database performance bump is that you can save up lots of server costing. So server costings, then again, like I said, that it's really going to be amazing for large companies that that query over 10 million or even 100 million queries every month, to be honest. So this is one. Secondly, when you're building a RAG application, you have to manage through or tackle through multiple layers of services, right? So for example, you need to be able to use something like a ChatGPT API, or you can use something like Olama for offline. then then you're going to have to be able to bring in your vector database to store your custom data, and basically make the search work for make the search work on custom data to be able to retrieve the appropriate knowledge, right? So basically building custom AI memory with the help of vector databases. And to be able to store them, you're going to have to vectorify them. So what happens is that there are so many processes that you're going to have to go through, right? So you have raw data, and then you're going to have to vectorize them, right? And then you're going to have to store them, and then you're practically going to search all of this, right? Search for data, and then you have something like LLM APIs that you can access using the ChatGPT API, or you can use the Cloud API, or you can pretty much use something like Olama for downloading. So what Antarys does is that it takes in all of this, and you can access all of these services directly from one application. And what I'm trying to do different is that I'm not only trying to build a vector database, I'm also trying to build the pipeline, so you can pretty much just directly input your raw data and it will be stored automatically. So this cuts in the latency, right? So first of all, it solves the latency issues. You are saving fractions of performance per vector data. So this, if you scale it up to millions of documents, it's really going to affect a lot for server or infrastructure pricing. Secondly, you are not going to have to juggle through multiple services, and you're not going to really have to pay for multiple services all at the same time to be able to build simple RAG applications. So this is another that. Third is that you are pretty much getting like most of the APIs that you're going to have to find through different services in one application. And for example, and this is a way for you to be able to run your own AI offline, for you to be able to store your data offline, and you can also access small language models all offline. So this is basically what I'm trying to do for Antarys. So yeah, the models are, yeah, there are some other explanations that I'm going to have to do. So for example, the model itself can be the bottleneck too. It's not just the search. For example, let's just say that, yeah, I'm going to go back to the example of the law firm, right? So all of these large language models, they are extremely bloated, right? So if you think about the DeepSeek 7B, or you can pick up any other models like Olama 3, 7 billion parameterized models, they have a lot of unnecessary information. So for example, if you're building an application for the law firm, but it doesn't really have to know about what is the capital city of Bangladesh. It doesn't really have to know about all of these things. It only has to know specific things about the law firm. So this is where the small language models are coming in, but they are much more fine-tuned to do their specific tasks, and they are just much more fine-tuned to be able to do whatever you want them to do, right? So the way that I think is that small language models, or even large language models, are very good conversational holders. Like, they're very good brains, right? So we can talk, but the actual magic actually comes from the AI memory. So all of the data that are stored in the model itself, or basically you add custom data on top of that via vector databases, right? So you have all of these things together. So what if I shrink down the additional knowledge of these large language models? So I distill memories or distill knowledge from these large language models and convert into very much precision or very much specified smaller language models, right? So this actually makes a lot of sense, because you don't really have to carry over or pay for much more infrastructure or server pricing, and then you have access to much more specialized smaller language models, right? So these small language models are very good at what they do. They're not very much generalized, but they're much more specialized. So what's going to happen is that you can pretty much host everything by your own. So this brings you the opportunity to do privatized or very personal AI development. So that's one crucial point. And the other one is that the model itself, like I said, it can be very bloated, it can be very generalized, but otherwise you're getting like specialized models. So Antarys is going to move towards that. I've been very vocal about small language models, and Another thing that I'm trying to plan is that small language models with a marketplace where you can pretty much access these custom knowledge graphs from the Antarys itself. So you can pull in custom knowledge graphs. So your AI can be knowledgeable on facts that you can later on download. So these facts or these knowledge graphs are basically components to your AI, if that makes sense.
Okay, so I have just one worries. Like, okay, so like till now it was a really informative session with you. So just like what skills should a student or a working professional should have to start learning now to work on vector database, or how can they work effectively with vector database? Like, is there any kind of roadmap, or uh, from where they can start?
Yeah. Okay. So I think at this point, so before AI, what developers were using was Stack Overflow, to be honest. And right now we're just using ChatGPT or Claude, right? So even then, developers were actually struggling. There were copy paste developers who were just copying answers from Stack Overflow and trying to paste them into the code base itself. And there were a lot of developers who were trying to do that. And yeah, and right now what we're seeing is that a lot of developers are just copying code from ChatGPT and then pasting them over to their code base. And believe me or not, a lot of senior developers do that. Even I do that. A lot of the code that goes into the Antarys code base, uh, a lot of the theoretical parts actually, I took the help of Claude. Claude is really good at research and stuff like that. So I think what's going to differentiate the good developers from the bad developers is the understanding of how computers work. So it doesn't really matter whatever you're trying to do, even if you're trying to build web applications, even if you're trying to build mobile applications, even if you're trying to build a vector search, or you're trying to work within this space of AI or whatever you want to do. Just and if it's computer oriented, just make sure that you understand how computers work first, and then you also have to make sure that you understand how logic works, right? So, for example, syntax is much cheaper. To be honest, you can always learn syntax, and even if you are struggling with syntax, I'm going to give you one very interesting thing: is that most of the PhD holders who come up with all of these interesting algorithms, they're really good. They're really bad programmers, right? So they code in the most disgusting way. They just make up a lot of code and just try to do what their algorithm is trying to do, right? So they write a lot of pseudocode. I think this is something that, apart from learning computer science fundamentals or basically how computers work, is that you can also try to learn logic through pseudocoding. So this is really important for me. So for example, this is the code base of Antarys, right? This is basically some of the APIs and stuff like that. But when I try to build a new feature, what I do is, yeah, I was just writing this code just a couple of minutes ago when I went on the live. So whenever I try to come up with new features or new, um, like even if I'm trying to fix bugs, what I do is I print out or write out the whole logic in a pseudocode language, or it's just me trying to map out what I really want to solve and then break down the problems and then approach it programmatically. So this really helps me build applications and pretty much map out the features even before I write the actual code. So I already know what I'm trying to do. So this is what you need to do. You need to be able to understand computer fundamentals, and specifically you really need to understand memories and pointers and data structures. So these are like very important concepts, but these are also very basic concepts. And then you're going to have to be really good at logic. And you don't have to be a competitive programmer, or you don't have to be like building all these fancy projects on GitHub or something like that. You don't have to do any of these things. You just have to be able to like take down the problems, break them down into smaller problems, write it down, visualize it, and then approach it programmatically. I think you're going to be able to build amazing applications. Even if you think about complex projects like compilers, or even like this one, this vector database is an extremely huge code base. So if I show you just the API, go, yeah, it's a really huge, it's a really huge code base, right? So how do you manage all of this? The only way that you can manage extremely large code bases is through breaking down these problems into smaller problems and then approaching it programmatically. So yeah, these are some of my tips to get better at programming or even get better at just solving problems in real life. Another thing I'd say is that try to write some low level code. And nevertheless, it doesn't really matter what sort of programs that you're writing. If even if it's mobile applications, even if it's like web pages, I think that you really need to understand how memories work. Because if you think about everything, every computers, these are all controlled by memory, right? So if you can manipulate or basically manage memories by yourself in computers, you can like really get to building amazing applications like this. For example, if you write something like, I don't know, Python, right? So you can create something like x10 equals 20, and yeah, you are pretty much in a higher level language. You don't really have to manage the memories by yourself, right? So but in a lower level language, for example, Zig, what you're going to have to do is you're going to have to create something like const x equals to, let's just say that I want to, I'm writing pseudocode again. This is not actual code, but you're going to have to use an allocator, and you're going to have to allocate some memory into on top of it. So if I wanted, right? So if I, okay, differ allocator try. So this is very different from writing an actual Python code, right? So again, I need to do this. I actually need to assign a value. So x dot equals to 10. So what am I showing is that, let's just say this is Python, and you just create this variable. You don't have to worry about like if I'm saving all this space in the memory later on in the program, because Python's interpreter is going to take care of that. But when you write programs like this in low-level languages like Zig, you're actually going to have to create the memory block. You're going to have to remember to destroy the memory block after you've used it to give the memory back to the system itself. And you're also going to have to assign a value to the pointer, right? So this is what I'm trying to say is that first, learn the computer fundamentals, how it works. And memories and pointers are really important concepts. And you're also going to have to learn about data structures, how to efficiently store data in complex structures. This is really going to help you out in the programming career. And the second thing is to be able to like take down complex problems, break it down, write pseudocode as much as you can, or just try to print out. Even if you want, you can build flowcharts, even if you want to. So yeah, the second tip is to be able to like just break down the complex problems into smaller problems. So, and third, try to not focus in one program language. I think a lot of programmers that are learning to code just now, they love to focus on just, yeah, I'm just going to use this program language for the rest of my life. No, it doesn't happen. It doesn't work like that. I myself have written like so many languages, even in my career, even in my free time. But the most of the common programming languages I write is the JavaScript, Python, Golang, Zig, and some C, C++. So if I just take you to sorry, just go there. So this is the repository of Antarys, and as you can see, that I have a lot of different language-based stuff here. So the Antarys code base itself is written in Golang. The benchmark, yeah, this is done in Python. I'm also writing a version of Antarys that doesn't really rely on garbage culture, so that is written in Zig. I have some other projects and stuff like that. The Antarys Node SDK is written in TypeScript, right? So as you can see that you're going to have to tackle a lot of programming languages in your life. So a lot of newcomers, what they do is that they love to focus on one specific program language. So yeah, you don't really need to be able to do that. Just master one language really well, and yeah, learn the logic and practice as much as you can, and try to be open source. So yeah, these are my basic tips, I think, and this can really help you out in the programming journey.
So it was an actually amazing session with you. So, do you want to share with us more, or should I conclude this here?
Um, it's really sad that we don't really have a lot of we don't really have a good startup ecosystem in Bangladesh. It's really sad. It's really saddening, and this is really driving out the innovation out of the country. So I think a lot of we need to be able to build actual or you know the problem I think is also it also derives from a lot of the university curriculums. To be honest, these are like very complex issues. To be honest, this is another live, right? If I dive in this topic about like the startup ecosystem problem in Bangladesh, the lack of investors, the lack of innovation, I think this is going to be another live. But yeah, what I'm just going to say is that if your talent is worth it, just go global. And people don't really care about what sort of university backgrounds you have. If you, how old are you? People really don't care about that. If you're good at your craft, and if you're building something that really is impactful, you can really scale it up, scale the product. So just my conclusion would be to be able to just become crackhead engineers, try to write code as much possible, and yeah, don't really focus on the university curriculums because they are very slow. They really are. It doesn't really take 4 years to be able to learn computer science. I don't think it should take that much time, because most of the really good resources are out there, and they're mostly open source. So if you want to do something like challenging, there are so many good platforms. Let me just show you something. It's called Code Crafters. So this has like really interesting challenges. So you can build your own shell, you can build your own Redis, you can build your own Kafka. Like, these are very complex projects, right? But they guide you through the whole thing. Then you have something like build X in Y minutes. Sorry, build your own X, right? So yeah, you can pretty much just take any of this project and just start doing it. So for I think a lot of the developers, or a lot of the engineers, even I made the same mistake, is that I believe in prerequisites, right? So by that I mean, uh, for example, if I wanted to build a gaming engine, I'd probably think to myself, oh well, I don't really know how trigonometries work. I'm not really good at trigonometry, so I'm probably not going to be able to do this. But most of the good engineers I've ever met in my life, yeah, Himel, can you still hear me? I think it's
Yeah,
lagging a
yeah,
bit.
I can hear you.
Okay, okay, yeah. So most of the good engineers I've met in my life, most of them, they didn't believe in prerequisites. They just went in and started building it, and you're just going to be able to find resources, or just learn stuff on the go. So this is really important. Even when I started building a vector database, I didn't really have much idea on graph data structures. I didn't have much idea on how HNSW worked. I just learned it and built it all at the same time. And common sense is a much have it's a very important thing to have, to be able to like take down all of these complex problems and just part them into small problems. So yeah, these are just my conclusions. Don't be afraid to just go ahead and building something. I know engineers with backgrounds in law. I actually used to work with an engineer who used to be a doctor. So it doesn't really matter where you come from. What really matters is that how can you take big problems and can chunk it down to smaller problems and just start building it. If you are afraid of like prerequisites, that I have to know XYZ, for example, I have to know calculus, I have to know linear algebra, I have to know all of these XYZ things in order to be able to start building this, you're just going to fall behind, because there are someone out there who are not afraid to just go in and start building stuff.
So this was truly a great motivation for us, all of us. You were actually telling me in the DMs like, all you need is to be some crackhead to do something in life. So
Uh, yeah, you don't really have, by crackhead, you don't have to be able to put out or write code like, I don't know, every waking hour. You don't have to do that, to be honest. But I think by crackhead, all I really mean is that you're not supposed to be afraid of building things. Big applications, they are quite scary. For example, like if I think about building a compiler today, it sounds like a lot of work, right? So if you break it down, if you break down compilers, you're gonna have to build an interpreter first, and if you have to build an interpreter first, you're gonna have to learn how to build a parser. So these are just incremental knowledges, and in order to build parsers, you need to be able to be good at regexes. So you can break down stuff like this and just start building, right? So first you need to get good at regex, and then you can build a small parser, and then from that parser you can extend it to become build an interpreter, and then you can use something like LLVM to be able to build your own compiler. You don't really have to be afraid of it. So that's what I'm saying, is that don't be afraid of building things. Just go ahead and do it. You're going to have fun. Believe me, if you like computers, you're going to have fun.
so thank you so much, Adi, for uh, having. It was great actually having you with me. So I hope if any of you have any queries, you can DM Adib directly, or also check out Antarys AI. It is also available. I will provide the link later on. So thank you so much, Adib. It was great having you. So this is for today. Goodbye, everyone. Thank
Bye
you,
bye.
Adib, once again. Bye bye.